the setup was there.
Ja, kommt, Stefan. Ah.
Perfect. So,
stage is yours.
Thank you very much. Welcome everybody, and thanks a lot for the introduction, also for the invitation to speak here today. The title of my talk was very generic because we did this a few months ago and didn't really know yet what to talk about. But what I would like to focus on today is a particular area of application, which is quantum optimization. And I heard also in the sessions this morning that there's some interest and also some work going on in this area. So I hope the part is also interesting. To start with, there are different types of optimization problems that we look into, and I want to focus here on a subset. Usually when we talk about optimization on a quantum computer, it's discrete optimization, more particularly binary optimization. There are also some other suggestions, but this is let's say the problem classes where we hope that there will be some advantage in the next time. And I split this further. First, there's Blackbox optimization. This usually means we don't have access to gradients. In practice, it's usually like some complex function that we implement to evaluate it. So we just have some input, some bit string that we put into a function, we get back a value. That's usually the most difficult class classically because you don't have any structure to exploit. Then there are two other classes, non-convex and convex optimization. Actually, an example of this is in both cases a cubo. So you have some matrix and you just apply the binary reactor from left to right. And if Q is positive semi-definite, that's convex. That's quite nice for classical algorithms. If it's not positive semi-definite, it's non-convex, and then it's already a little bit more difficult because you cannot work with continuous relaxations. So this is a class we focus on most of the time now, but I later also want to get back to Blackbox. And the reason is that this is already a very interesting class. As you're probably familiar with, it's an NP-hard problem class in general. You can model many interesting applications like portfolio optimization. We saw already some routing application earlier today. And you can also model some variants of feature selection. All right, so just to give everybody this background, probably most of you are familiar with that already. Usually we look into two different formulations of this problem. First is this quadratic programming formulation that I started with, but we also sometimes need an Ising Hamiltonian to translate it more into the language of quantum mechanics. So what we do here is it's a relatively simple set of steps. We replace our binary variables by this plus minus 1 binary variables. Then we replace this by this Pauli matrices, or tensor products of Pauli matrices. So we translate this in a large matrix, and I'll show an example in a second. And then, instead of solving this optimization problem, we're looking for the ground state of this Ising Hamiltonian. So we translated it from the binary optimization into a ground state problem. And this is what quantum chemists, for example, do all the time. So there are algorithmic or suggestions of algorithms how to approach that. And we will look into that in a second. All right. So here, a very small example. I use this throughout the presentation also to illustrate some of the algorithms. You see it's a very simple cost matrix. It's 3 binary variables, and you can easily see that the optimal solution is this one. If we translate this now into an Ising Hamiltonian, it would be this representation. So it's still a relatively compact representation, but if you really write it out, which we never do in practice, you get this exponentially large matrix with all the possible combinations on the diagonal. And here in this case, the optimal solution will be this one, which corresponds to this basis state, and you see that this is corresponding to the optimal solution. So it's equivalent representations of this problem. All right. There are different algorithmic primitives that can hopefully lead to an advantage in quantum optimization. We already heard about Grover search, which is a special case of quantum walks. There's adiabatic annealing or quantum annealing, which then also leads to some heuristics. And there's imaginary time evolution. And I want to quickly go through that, the first two relatively briefly, and give some idea why I think they are more or less suited for near-term applications. And then the last one a little bit more detailed. So for Grover search, Most of you are probably familiar with that. So we assume we have some function which goes from a bit string or from this integers from 0 to 2 to the n minus 1 to a binary value. And then we have an oracle. We heard about these quantum oracles before that maps the quantum state, basic state here, to this one. So if this function is 1, it multiplies a minus 1. If it's 0, it does nothing. And then Grover search allows us to kind of invert this function. It allows to find an element where this function is 1. And it does so with complexity of square root of 2 to the n. So that's square root of brute force search. And we know that classically that's actually the best you can do, more or less, even if you randomize. So it's a quadratic speed up over brute force search. Now there's Grover adaptive search, and we saw this is also available in Planck, as I've seen in the slides before, which essentially uses this, but in an adaptive way, to in every iteration look for a solution that improves the function. So this is now not a binary function anymore, but it gives us a certain value. And now we're looking for the minimum of this function. So we start with a random value. This gives us a certain function value, and then we construct an oracle that just flags all the values for all the states that improve upon what we already know. And then you just iterate until you can't find a better solution. Now, Grover search is very nice because it gives a quadratic speedup. So that's beautiful from a theoretical point of view. We know that these oracles can be constructed efficiently for QVOs. So also like from a practical consideration, this is interesting. However, these circuits become really deep. We get a quadratic speedup, but square root of an exponential number is still a very large number. So this is a problem, and this very likely implies that it requires a fault-tolerant quantum computer. So it's certainly not a near-term algorithm. The second point, sometimes also forgotten, fault tolerance introduces a huge overhead. So a quantum computer with error correction runs significantly slower than a near-term quantum computer or a classical quantum computer. So quadratic speedup is nice, so you need significantly less operations, but every operation is significantly slower than the classical counterpart. So the kind of the break-even point where the quantum computer then really outperforms the classical one, very likely only for extremely large problems. So which then requires even longer circuits. So it's very difficult to see where this really has a practical impact. So Grover search, I think, is very nice from a theory, but this is something one should never forget. That it's not clear when this really will get an advantage. All right, so the second algorithmic primitive is adiabatic annealing, and this is based on this so-called Adiabatic Theorem. I'd like to quickly read that through. It's quite technical, but then I introduce it a little bit more intuitively. So the Adiabatic Theorem says that a physical system remains in its instantaneous eigenstate if a given perturbation is acting on it slowly enough, and if there is a gap between the eigenvalue and the rest of the Hamiltonian spectrum. So as I said, it's like a quite dense statement, but I'd like to, it's really the basis of all these quantum annealing and so on, so I think it's important to have seen it once. So what this means now, or this gives rise to quantum annealing, and what we usually do is, if we have a cost Hamiltonian, so this is now what we constructed for our problem, we find a simple Hamiltonian with an easy to prepare ground state, and this ground state should have a non-zero overlap with the ground state of our cost Hamiltonian, so with our problem. I'll give an example in a second. Now, what we then do is, we start in this ground state, and then we drive the system from this ground state by applying this dynamics and by changing the Hamiltonian slowly to the ground state of our problem. And what the Adiabatic Theorem tells us is that if we construct a very simple optimization problem, that's essentially that, where we know the optimal solution, and if we very slowly change this optimization problem, we always stay in the optimal solution of this intermediate problem, and if we in the end finish in our target optimization problem, we are still in that ground state. And common choice is the following: the sum of this Pauli X matrices, which is illustrated here. So the white part is 0, the other is -1. And the initial state is the equal superposition state, which is the ground state of that. It's very easy to prepare. And since it has contributions of all basis states, it also has an overlap with the optimal solution. And I implemented that for this illustrated example. And you start here at the ground state, then you anneal, and then you end up here with the optimal solution of our problem, which gives a target energy of -2. Alright, so that works, and I solved here the ODE, this one, and just to test, I also computed the ground state of all the intermediate Hamiltonians, and like they nicely match, so this seems to work well. The second part is here, the spectral gap. So this is the difference between the ground state and the first excited state of these Hamiltonians here over time. And you see this getting smaller, the end is getting larger again. Here, at the smallest point, it's like 1.3 or something, so this is all good. But this is now really the problem, because if we make this problem larger, this gap tends to decay exponentially fast to 0. And as you've seen in the Adiabatic Theorem, having this gap large enough is actually a requirement for it to hold. And what's happening if this gap becomes small, and if you anneal too fast, is that you jump to excited states, and you jump to an excited state somewhere here in between, and then you end up a completely different solution of your problem. So what this means is that in practice you have to anneal exponentially long, or because of decoherence you usually cannot do that, you have to do an exponential number of shots. So in any case, it's usually an exponential overhead. Alright, now, anyhow, let's suppose we want to implement that in a quantum computer. I don't want to go through the math here. You can, you need to trotterize this operation to map it to quantum gates. What it essentially means is that you have here, for every term in your Hamiltonian, you have a gate. And for every 2 body terms, you have a 2-qubit gate. And then you repeat this a number of times that depends on the annealing time. So if you have long annealing times, then you need to repeat this many times. So it's not really practical because we run into decoherence and we accumulate too many gate errors. One way to work around that is the Qia algorithm that I've heard people mentioning already today a couple of times. And the idea is that we don't repeat this like t times. We just fix a number, p, and we cut off. And instead of choosing the angles of these gates, following this annealing schedule, we just ask a classical optimizer in some training loop to find the best angles. And then this is essentially the Qia algorithm. It's motivated by this adiabatic annealing, by this adiabatic theorem, and it's a quite popular algorithm for testing optimization, or for trying to solve optimization problems on a quantum computer. It's essentially just a special case of this variational quantum eigensolver where we use problem information to construct a problem-specific ansatz or problem-specific circuits. But because we just truncate, it's essentially heuristic, so we do not have any guarantees about the performance. Now, in a recent paper from February, I think, we tried to understand how this algorithm actually scales. And here I'm not talking about the performance. As I said, it's a heuristic. Like how well it performs is something we have to try. But what we can do is we can make some necessary assumptions, not necessarily sufficient, but where we know if they are not satisfied, then there's little hope for quantum advantage. And we made these assumptions and tried to answer these questions here. So what number of repetitions do I have to choose for a particular problem? What's the number of gates and the resulting circuit depth if I then compile this to a particular hardware connectivity? And we have heard about that from Marie in the previous talk. Then if I have the depth, how can I translate this into runtime? Like how long does this algorithm really run? For this I also have to take into account the optimization, how many steps do I have to do in this optimization loop? How many shots do I have to do? How does the number of shots scale with the problem size? So there are many assumptions or many things that play into that. And then if I have the circuit depth, I can also ask the question, how well does my my gate fidelities have to be, like what's the noise that's still acceptable to run this circuit. So this is quite related to the NISC analyzer that we just heard. And we went through this in quite some detail. I don't want to go through all of that now, but essentially give you the results. First, we looked into the runtime, and let me quickly walk you through these assumptions. Some are on some theoretical considerations, others are empirically. First, we say that the number of repetitions, p, is logarithmic in the size of the problem. This is a necessary condition because if we choose p fixed, then there are some proofs that you, for some problem classes, you can always beat that with a Duman-Williams algorithm if we talk about max cut, for example. So there's some classical proofs that, some theoretical proofs that if you don't increase that, let's say at least logarithmically, you'll beat that at a certain problem size. And the second assumption here is how many optimization iterations do we have to do. There we did some numerical tests and we came up with 25 times p. So it's linearly in the number of parameters that you have to optimize. Then the number of shots. This is already way more difficult. From a theoretical point of view, we think that depending on the problem, it should scale quadratically in the problem size. And we made some tests and it fit and it looked like 100 n squared. But for some problem, you might be fine with just some additive fixed threshold or error threshold. So we also thought maybe for some problems, some constant number of shots is sufficient. The truth is probably somewhere in between, so this can be seen as an optimistic assumption. This may be a bit of a worst case assumption. And then the gate duration, we look here, we did differentiate two cases again. The best realized in the literature is 30 nanoseconds. So this has been demonstrated for small test systems in the lab. Our current hardware is more of the order of 400 nanoseconds at the moment. So again, it's like the best case in the actual case scenario. If we translate all of this, this is now for a dense problem, so if this cost matrix of the quadratic program is dense, then this is what you get. So in blue, you have the 400 nanosecond gate times, in red the 30 nanoseconds, and the solid line is 10 to the 4 shots, while the dashed line is 100 times n square shots. And you see that if we are here optimistic, and we go up to 500 variables, then the runtime is already like 1 hour. If we are less optimistic in the gate times or in the shots, then this can go up to a year. So if you think of that as kind of a confidence interval, then we are somewhere between an hour and a year of runtime, which is quite significant. So something we really have to take into account when looking for applications of this algorithm. We also looked into if we just assume there's no optimization necessary. And this is also 10 to the 4 shots, then we can get this in a few minutes. So sometimes if you have an idea about choosing good angles, there's also some research about concentration of optimal angles and so on. Like if you can pick these angles up front and just say I don't optimize, then you can get good samples possibly already in a few minutes. And you can create many of them, so there might be applications, or maybe you do some classical post-processing, some local search, I don't know, where this might be interesting. All right, the second question that I want to answer here is the requirements of the gate fidelities. It's a pretty technical slide. So the noisier the gates, the less of them I can of course apply, and with the limited connectivity I need to insert the swaps and so on. So this is all limiting how dense I can choose the problem, or how dense problems I can look at, and how many repetitions I can make. And there's a nice paper by Franca et al. Which introduces a criterion for that essentially. So this is going a little bit beyond the coherence time. It's really looking at the 2-gate or 2-qubit gate fidelities, 2-qubit gate errors. And what this essentially does is it gives you a threshold, an upper bound on the number of gates that you can afford with this noise level. And what does it mean to be able to afford that? That means if you want to get the energy, like the objective that you minimize during this variational algorithm, if you want to get that epsilon close or epsilon accurately, And if this is your gate fidelity, then that's the maximum number of gates that you can run, because otherwise, if you go beyond, you can actually get a classical Gibbs state, or you can classically sample from a Gibbs state that gets close enough. Because your circuit will be so noisy that like the quantum or the interesting part is gone, and you can just do it classically. And we illustrated that here. The x-axis is the density of the problem. So 0 would be no problem, and 1 is if this cost matrix is dense. And this is the single C0 gate error. And then essentially these are kind of the frontiers at an accuracy of 10% for QAOA 1, depth 1, 2, and 3 for 485 qubits. So to run QAOA on this almost 400 qubits, this is with depth 3, this is the required fidelity if your problem has this density. This means here you're already well below 10 to the minus 4. Currently we are somewhere around 10 to the minus 3. And if you want a dense problem, and practical problems are very often dense, this is a bit of an issue. Because as soon as you have some constraints, you square many terms, and this introduces the density of the problem, or increases the density of the problem. So practical applications are often more on this side here. And so the fidelity requirements for the 2-qubit gates will be pretty high. Now, for error correction, the threshold is usually assumed to be 10 to the minus 4, so if we reach 10 to the minus 4, then we think we are in a regime where error correction will scale. And we think that we can reach that threshold. But I'm not sure whether we will push it that much further. So 10 to the minus 6 seems pretty, I don't know, I'm a mathematician, but I'm pretty sure our experimentalists will run away if we add such a requirement. All right, so this is for standard QAOA. Now, we built a QAOA runtime program. The Qiskit runtime has been mentioned before, which essentially does a lot of optimization, circuit optimization, native gate decomposition, so that the gate is decomposed into pulses, some error mitigation, and so on. And you can apply this then via the API, and you don't have to do all these optimization steps yourself. We did this for a 27-qubit example, where we now did a hardware-native graph. So this is the coupling map of the hardware, and the cost function has exactly the same structure. We did a max cut problem on that with signed edges, so the edges have plus minus 1 weights. And for QAOA depth 1, we saw relatively nice convergence. And you see here the sampling behavior for in gray random, and in blue after the optimization, where the optimal cut would have been 12, we achieved the 10, so it's not yet getting the global optimum, but it's working relatively nicely for depth 1 QAOA. And we tried depth 2, and this is what you see in red, and this is essentially just random sampling. And if we apply this fidelity criterion with epsilon equals 10%, then we should be able to have 13 C0 layers. Depth 1 had 6, so depth 2 would have 12. So in principle, it still should have been feasible, but this fidelity criterion is still it's a little bit optimistic. It's only looking at 2-qubit gate errors, not considering crosstalk, and also not considering coherence. All right, so to conclude on QAOA, this mapping from dense problems to sparse hardware, this is really a killer. So at the moment we can run problems that match the hardware connectivity, but if we really have to do all these swaps, and for dense problems our swap strategies are pretty optimal. So there's not much to gain. So that's one thing. The second, even if we can apply it, the runtime will be pretty significant, particularly for dense problems. So we have to be careful in the applications. If you are interested in some real-time application, I mean, sometimes you read something about high-frequency trading or something in the press, this is definitely not an algorithm for high-frequency trading. Now, that may sound a bit pessimistic. There are some variants of QAOA. You can change the objective function, like using conditional value at risk. You can use recursive QAOA, warm starting QAOA. These are very nice candidates. These might break some of these problems because, for example, the recursive QAOA, with recursive QAOA, we don't necessarily have to go to a logarithmic depth of the circuit, but we might be able to have some constant depth. And warm starting QA already starts at a better solution by leveraging classical algorithms. So there's still some hope, but I think these things about the requirements on the gates and the runtime is something one really has to keep in mind. Now, the algorithmic primitive that I find at the moment the most exciting and where I think we have the best chances for a near-term advantage is this imaginary time evolution. And let me very briefly explain what this does. So, I mean, you may be familiar with real-time evolution. This is like the original suggestion of Feynman to what to use a quantum computer for. And what we do here is we replace t by this imaginary time. This is just a mathematical trick, so there's no imaginary time. And you end up with this term. So it's just e to the power of minus your Hamiltonian times t. If you evaluate that, it looks like this. And what happens is that large eigenvalues are actually suppressed, are decaying very fast, exponentially fast, while small eigenvalues are actually, in this case, even amplified. So it's really pushing the weight from to the solutions you are interested in. And then we normalize this again, so because this is not a quantum state, so we normalize it, and then this is actually imaginary time evolution. I applied this for this simple example, and you start again in the equal superposition state, and this very quickly decays to the optimal solution. This is what's happening with the state, so this is the equal superposition state at time 0, then already at time 0.25, you see that the optimal state has the largest weight. The second best also have a large weight, or a larger weight, actually a weight that's amplified compared to this here. The rest is already suppressed a bit, and then at time 1, the optimal state has already a very high probability, almost 1. The second best have a small, still a tiny bit of mass, but the rest is gone. So this is really nice. So this is suppressing the bad solutions and amplifying the good ones. Can also be written as this differential equation here. Again, I don't want to go into the math, but we'll need that conceptually in a bit. So imaginary time evolution is working very nicely, but it's a non-unitary operation. So it's actually pretty hard to implement it on real hardware. And if it would be easy, then something would be wrong, because we know that the problems that you can solve with it are QMA hard. So that's the quantum version of NP. But what we can do is we can try to approximate it. And there's one proposal to do this using variational algorithms. And so we assume we have an ansatz. Let's say take this one. So 6 parameterized gates and some entangling gates. And what we do is we project the evolution of the state space, so this differential equation on the Hilbert space, to this space of the parameters. And you can do this using a variational principle. So essentially you project, or you update your parameters such that they track this state evolution that you are interested in the best possible way. So you project from the manifold of your parameter space here, or from your parameterized subspace, you project this update onto that manifold. And this differential equation for the parameters is given by the energy gradient and by the quantum Fisher information matrix. I don't want to go through the math here. I think it's important that this is 3 terms. So actually to evaluate this, you need to evaluate 3 circuits.
Is the gradient computed on the quantum, on the QPU?
You can,
okay.
Yes, yeah. There are parameter shift rules, for example.
No, are you doing it here? You're assuming Do assume this here that you do it on QPU?
Yeah.
Okay.
Yeah. These are all three terms here. You can evaluate with quantum circuits. And we have implemented that in Qiskit. And then if you have that, you can evaluate this differential equation for your parameters, and then you can solve this with your favorite ODE solver. Usually we use Euler, or even forward Euler, because all the more advanced ODE solvers actually not so nice if you have noise. And we of course do have noise here. Now, you might have heard about quantum natural gradients. It's exactly the same. So in our case, this is equivalent. Now, this is very nice, but there's again a practical problem. This is 3 circuits, but it's 3 circuits for every element of the quantum efficient information matrix, which is quadratic in the number of parameters. So this, since running circuits takes a while, this very quickly becomes prohibitive in practice. And then we developed a way around that, and we used SPSA, so Simultaneous, Perturbation, Stochastic, Approximation, which you might be familiar with as an optimizer for variational algorithms. The idea here is that, let's say this is the landscape of our loss function. You pick a random direction, let's say following this distribution, and then what you do is you do a finite difference approximation of your gradient in this random direction. So not for each coordinate, but just in this random direction, and then you multiply it by this random direction. This is nice because this is an unbiased estimator of the true gradient, so you can just, if you do this multiple times, on average you get the true gradient. And this now only requires function evaluation, so now we don't have to do a quantum gradients, but we can use that. Then the second thing is, this also works for second order derivatives for the Hessian. There you pick 2 random directions, you apply the second order derivative finite difference formula in these 2 directions, and then you get here this scalar, and you multiply it by this matrix that you build using these 2 random directions. And again, this is an unbiased estimator for the Hessian. Now, we don't really need the Hessian, but the quantum Fisher information matrix, but this can actually be seen or written as the Hessian of the state overlap. So, again, the math is not important here. We can discuss this later if you're interested. But this is a property that we can evaluate on the quantum computer with a single circuit, and then we can use the second order finite difference or second order SPSA to evaluate the quantum Fisher information using that. So instead of having a quadratic number of circuits in the parameters, we actually now have a constant number of circuits with respect to the parameters, and we can get these stochastic approximations of the gradient and the quantum Fisher information. So we can use that to approximate this variational quantum dimension time evolution, and this is what we did here. So you see the ansatz. Then in black here you have the imaginary time evolution that we have seen before. In red you have the variational imaginary time evolution, so it's the approximation using that ansatz. And then in blue you have the quantum natural SPSA, which is matching pretty nicely. And since we're interested in the ground state, here there's a shift of 2 missing, but since we're interested in the ground state, it converges very nicely. So this is the algorithm, but it has also another nice, okay, I think I summarized that. Okay, so I mentioned all of this except the last point.
Yeah.
So what is very, very interesting is that the algorithm itself does not impose any restrictions on the circuit. So we are completely free to choose the circuit. Of course, if we make a bad choice, the algorithm might also just not work very well. But I mean, in the tests that we did pretty random choices, and it already worked relatively nice. So I think it's significantly less demanding on the circuit than QAOA, for example. It has another nice property, and that is it can also be applied to black box binary optimization. So this is the problem class we solved earlier. We just have a black box that we can evaluate that gives us a score. We can interpret this then as an implicitly given Hamiltonian. So we just assume that the function value for all exponential number of inputs is on the diagonal. And since the only thing we need is evaluating this expectation value for our algorithm, this is immediately applicable. The problem we looked into for that is optimal feature selection. So we assume we have a data set with n features and m data points, and we have some machine learning model. It doesn't really matter what it is. The only thing we need is that if I select a subset of features, I can train my machine learning model and then I can score it. And then this is my black box. I select my features, I train my model, I score it, and this is my function f. And then, if we have that, we can use this algorithm, which is motivated from a theory to find the ground state, so the optimal solution of that. We tested this on the so-called German credit data set. This was a collaboration with PayPal, and they were interested in credit risk analysis. So that's why we picked that. It's a data set which has 1,000 data points, 20 features, 59 features after one-hot encoding, and then it's a classification problem. So essentially you have some anonymized people and you want to know whether they are trustworthy to give a credit or not. And we first looked into this where we restricted to a subset of 20 features, where we used then classical simulation and real quantum hardware on 20 qubits. And then we did a matrix product state simulation for the full data set of 59 features, or 59 qubits. And the ansatz we used is essentially this one, this real amplitudes ansatz, where we have single qubit Y rotations, then pairwise C0 gates, and then again single qubit Y rotations, and repeated this up to 2 times. And for these circuits, which are relatively shallow, the MPS simulator is still an exact simulator. So it's essentially in that sense, it's a classical algorithm if you want. All right, these are the results, and this is now for 20 features. And what you see here is the result of the training. It's a little bit a dense plot, and you have here classical algorithms, recursive feature elimination, and the resulting score after training the model. And then you have in green the solution of the quantum algorithm, which actually, you see this actually outperforms the classical ones, and it found the global optimum here. And the confidence levels are from some bootstrapping, confidence intervals. What you can do is, since the quantum state gives you a probability distribution over all possible feature selections, you can actually enumerate all of them, evaluate the probability, and then have a cumulative distribution function of the different scores. That's what you see in blue. So the trained state is pretty good, so it concentrates pretty close to the global optimum with some overlap. And this purple line here is the cumulative distribution function if you would just do random sampling. So you see that essentially the training went from this state to this blue state. So that's very nice. And here you see the training loss. This was on the real hardware, this blue line. Here's the training loss using the real hardware, so it's a little bit more noisy, but it's still converging to a nice value. And here, this is on the test data, where we have more or less the same picture, but of course on the test data, the score is a bit worse. This is for 20 features. For 59 features, as I said, we only simulated, but it's also converging nicely. And maybe here a comment: 59 features means 177 circuit parameters, means already over 50,000 circuits for a single estimation of the quantum Fisher information matrix. So that would really be not scalable if you would do this dark height exactly without this SPSA trick. And again, here we saw that the quantum algorithm actually performed the best feature selection. For 59 qubits, we cannot enumerate anymore, so we don't know whether it's the global optimum. And for test, it also performed similarly. All right. That was all I wanted to say on these optimization algorithms. I have a little bit more on how we actually implement or plan to implement them in the future, and some of this I added just over lunch based on the questions that have been asked earlier this morning. But before I get into that, any questions on the algorithms?
Does it make sense to have a warm static variant of the imaginary time thing?
You can do that. Yeah, we have.
Does it make sense?
Yes.
Okay.
Yeah, but you would have to do it in a bit different way. So not one-to-one. You can do it one-to-one, but you have to think a little bit about how you construct your circuit then, and it would mostly result in how you initialize your parameters. So you could set the first layer to 0, such that this doesn't do anything, and then bias these last gates towards some solution that you're interested in, for example. All right. Now, Frank, you mentioned already the roadmap, so I don't have to go into that much more. Maybe just one clarification. Earlier today, it was said that we want to build 1 million qubits. That is of course true, and that's what we want to do. But for now, we committed to up to 4,158 by 2025. I think this will be very exciting. But you see here that this will also require quantum couplings of different chips, and there we go through different technologies and so on. And this is currently being worked on. Which then, to also maybe reference the last talk again, will impose significantly new challenges on the compilers, the transpilers and so on, because then you have different kind of interactions, maybe a smaller connectivity and so on. What I wanted to emphasize here is once more the Qiskit runtime, but also these, here it's called threaded primitives, but these primitives in general, because I think this is very interesting and very important and addresses some of the questions of this morning. And at the moment we have 2 primitives. They're already available, you can use them. We have the sampler and the estimator. And it goes a little bit in the direction of the programming model question that we had this morning. Because this is now adding a new layer of abstraction. So in a way we add a more abstract or higher level or extended instruction set. I mean, this is some development that we went through classically as well over the times. And here it's similar, so we add these primitives. Essentially what you do with a quantum computer is sampling. It cannot do much more. Can summarize these samples and estimate some expectation value. That's also used in most of the algorithms actually. But then these are the two base actions that a quantum computer needs to provide, and ideally provide very well. If we have that, then we can hide all the transpilation, compilation, all the error mitigation, everything. We can hide all of this behind these interfaces, and ideally, the algorithm developer does not need to care about that anymore. Because if I want to implement my algorithm, I'm not an experimental physicist. I don't know how to tweak all of this in the best possible way. This should be hidden. And with these primitives, we're making an important step into this direction.
Stefan, what is a quasi-probability?
The quasi-probability distribution is one that has negative probabilities.
So.
And the problem is that after error mitigation, you don't necessarily have only positive values anymore. Because the error mitigation usually is not preserving that this thing stays a probability distribution. All right, so here I actually have a small example that I wanted to share. I actually implemented such a blackbox optimization using Qiskit and using this sampler primitive. And just want to quickly walk you through that. So of course you first have to authenticate yourself. We have this Qiskit runtime service, which essentially does that. You give a token, and then you can use it. And then, I construct an ansatz. That's a simple 4-qubit ansatz. And then now I can use this sampler. So what I do here is, and I ran this yesterday, you select the backend, you construct this sampler, and then after this with statement, you do something with this sampler. And here I just wanted to time it, so I just did 10 iterations. I selected random parameters, and then I just call this sampler for a particular circuit with a certain number of shots. And here I just take the time. And what you see is that the first iteration took about 6 hours. But then every following one was 13 seconds. This is the direction we want to take, that actually this thing opens a session, and once the session is open, or you have to queue a bit to get your session, but once you have it, you have for a certain time this reserved, and then you can really work with that. And in a talk this morning, one of the problems was mentioned that you always have to have the source code or ship the source code and put this in the Qiskit runtime program. With this, you can really develop your algorithm locally, but you still get the speed up of the Qiskit runtime via the session of almost the speed up. And this will make algorithm development significantly easier. The exact syntax, so this is not fully stable yet. This is working, this is implemented, you can use that, but it likely will change a bit over time. And like at the moment you select one backend, in the future you might want to reserve a bunch of backends and essentially define then your job comes in a queue, and then your whole job will be run, but the code might be actually executed wherever you want, whether this is in the cloud or in a Qiskit runtime program. You can also nest them so that you still have that running very close to the quantum computer, but you don't have to. And another point that was made earlier today was on latency. So for this Blackbox optimization, here I don't know, I'm not a Ray expert, but it seems to be a very nice framework to parallelize or put classical workload in the cloud. What I do here is I just have a black box that calculates the Hamming weight. So it just counts the number of ones as an example. But you could very easily also have here a machine learning model that you train and then score it and then return this number. And my point is, this can introduce quite some classical workload. So this can be heavy. And I have to do this for every shot, for every bit string that I see in this Blackbox optimization. So the bottleneck, the latency, is very likely not anymore the quantum computer. Because that's relatively fast circuits. I don't have to measure in multiple bases. I just want these samples. So whether then I have a little bit more latency to go from my notebook or wherever I execute this to the quantum computer, that's probably fine. I don't want to queue. So if I always have these 6 hours, then this doesn't work. But if I only have to queue once and then I can quickly go through that, then I think this is for many applications very interesting. And also for, if we think about quantum chemistry applications, the expectation values that we need to estimate there, they have very quickly millions of terms. So this is one call to the estimator and this will run for hours. Whether then I have a little latency in between when I call this, it's probably not the biggest problem at the beginning. Now to solve this problem, I wrote an objective function that takes the parameters theta of my ansatz, calls the sampler, then in this case evaluates this classical cost function for all the different shots, and then builds up the expectation value and returns the value. So this is the function that I then want to optimize, and here I did this on the simulator. I choose an optimizer. In this case, I just use Cobila because for this noiseless simulation, this is working fine with this sampler, and then I call the minimizer here. And the nice thing now is that because of this primitive session, this is happening without any queuing, or with only once queuing, and then the whole algorithm is running through. All right. And let me quickly check. I made some notes on the questions this morning whether I covered all of them. Yeah, okay. Good. So to conclude, I think quantum optimization is a very exciting field. There's just tons of applications, and if we could find only a tiny advantage with a quantum computer for these problems, there will be tons of applications. So I think that's very interesting, but it's still not clear how or when or where to realize that. And one thing that we just should also know, classical algorithms here are also extremely efficient. And the scale that we need to reach until quantum computers have a chance to outperform them, we will of course not see that at 100 qubits for most of the applications, but likely for many applications will require larger quantum computers. What QA is, or where QA is very nice, is that it really uses problem structure to construct a circuit, and this is something that we need to find new ways. So we need to find ways to exploit problem structures in circuit design, and this is something where I think we should focus more on, where we have too little understanding in how we can do that, like other than QA/OA. And in general, I think this quantum natural SPSA algorithm is a very, very promising candidate. So this is something we are currently investing, and because it's also so generic, like you can also look at black box problems. Black box problems are the most difficult classically, so we at least make it like more difficult for the classical side as well. So we don't necessarily know more about the quantum side, but we make it more challenging for the classical side. And another point, you saw the roadmap. We are planning to go up to 4,000 qubits. I think with this we reach a scale, and also like quality and speed of the hardware, where we can do really interesting benchmarks. At the moment, with 20 qubits, we likely just see like this finite size effect. We see the initial noise. But if we then scale, for example, to 100 qubits, I think that we really see the scaling of algorithms. So that's when we can really start to make predictions about a potential advantage. And the last point, I think is new primitives. This also make it very easy then to develop these, and I think way more efficient to really run these benchmarks in a reasonable amount of time. Because like for some of these experiments that we did, if you have to wait a week, then you don't do systematic benchmarking over a large set of problems. All right, and with that, thank you very much. And
so thank you very much again. And of course we want to open, if there are any questions from the audience. Frank already had some questions in between. Is there a question left? Tons.
Nobody else had. What kind of further primitives do you envision? So I assume we will have in the future a repository of primitives and so on.
Yeah. So, for example, for the estimator, there will be a bunch of estimators. This is now the simplest one, where we do some grouping of the Pauli terms and then measure in these different bases. But there are other things like classical shadows or some randomized approaches, which, if you have a large number of bases you need to measure in, can do this more efficiently. So this is something having different variants of estimators, which for different types of problems might be more suitable. And then of course needs to also be automated to select which one is best suited for the problem. And then one thing we already work on is a fidelity estimator, like state overlap. This is something that we use for quantum kernels, for example. This is exactly that functionality. If we have that as a primitive, then you could feed the primitive to the quantum kernel and run that. And you can implement that with a Hadamard test, with a swap test, with this compute-uncompute. So there are also different variants, and for most of the applications we cannot run the other variants yet because they become too expensive, but in principle they would scale better than the compute-uncompute. So at some point there might be like we get to a point where these other implementations might be more suitable. Gradients.
Sure.
Yeah. So these are things we're going to be thinking of and started to build already.
Thank you. One next question was, we also took a look at Classic. It's a tool builder, and they focus on circuits with hundreds of qubits. Okay. Anything that we may expect in the visual tool that you have? Yeah. So if you design circuits with hundreds of qubits, but the graphical representation gets cumbersome, and these Classic guys, they contract parts of the circuit provide them as reusable modules. Is that also something you envision?
In a way, we.
Yeah.
I'm just thinking. So in.
No, so the one answer may be that the graphical programming paradigm is not suitable from your point of view.
It is not, but it sometimes helps, and you can still go beyond, like to hundreds of qubits if you don't really go to the single X gate.
Yeah.
And if you use Qiskit today and you use this ansatz, you will not get individual gates. You will get a box, and it's only synthesized later on. And at the moment, the graphical representation still shows all the qubits, but I think it would not be a big deal probably to just compress this and say, this is one box and this has a line with, like, that corresponds to 10 qubits. But I think the graphical representation probably has to be changed at some point, but my argument is less that it's becoming too cumbersome, but that with dynamic circuits, you add additional logic that you can't even represent anymore. And so we need to go somewhere, like we need to extend this to somehow look at open quasar mechanics.
Thank you.
So we just come over there.
Thanks. So I find the idea of the Qiskit runtime environment really charming. It reminds me a lot of like stored procedures in databases. I wonder from the viewpoint of the provider, it must be difficult though, because you get a hybrid program and you don't know how long it's going to take for scheduling your system. I wonder whether there are opportunities for static program analysis in there, so that the provider gets an idea how many shots are going to be fired, especially if it's like a recursive algorithm, right? Are you working on that? To look at the Python program that you're getting and give a cost estimate for the whole entire hybrid algorithm? Because you're no longer just having the customer pay for the quantum part, you now got to charge them for the classic part as well.
I mean, there's quite a business question behind your question, and I can put you in contact with a product manager of the Qiskit runtime. He can
but it's also a software analysis question.
Yeah, right? it is, but so definitely, yes, that would be interesting. I don't think we are doing anything like this at the moment. I think at the moment what we are focusing on mostly is getting this interface right for these primitives and so on, and then you have to say how long you expect your program to run, you will, one can think of you also having to pay for this reserved time.